Hello, I'm Tim Lindquist, and this is SER 321, Foundations of Principles of Distributed Software Systems. And today what I'd like to do is to go over the section on sockets, which is Unit 12. So in the last session or last unit, we looked at threads and sharing data synchronization between different threads. And this time we want to look at sockets. We actually have looked at simple sockets previously in the network addressing section, but this time we're going to combine together threading and sockets so that in fact we are able to implement servers that are able to deal with multiple clients simultaneously. And what we'll do is each time that a connection arrives, we'll farm that connection out to a new thread, create a new thread, and give that connection to the thread for that thread to manage. So there are some pretty good references in both of the books for the class. Java Network Programming 4th edition in Chapter 8. It considers sockets, and Chapter 9 is also sockets chapter. Chapter 9 deals with servers, and Chapter 8 deals with clients. In Chapter 5 of Java Network Programming and Distributed Computing, he covers UDP, and then in Chapter 6, TCP/IP is covered. So either one of those books are a good reading reference for this section. We're also going to also encourage you to make sure that you've looked at the class notes, and I'm just going to follow the class notes actually pretty closely for this. So this is the last set of material that you need in order to do the download server for your Java Media client or media browser, server and browser. So the idea is to end up with a server that provides for the media library that's written in C++, and a server that allows you to download media from the server to the client. And that download server uses TCP/IP connections and is written in Java. Now for assignment 6, you don't have to worry about uploading, although it's another interesting possibility, right? So when a client adds a new entry to the media library, you could certainly have it at that point in time. The client would upload the file to the server. But we'll just if we can get one direction to work, and actually with only one of the clients as well. Assignment 6 does not require that work with the C++ client. That if you can get it going between Java and C++, that will be fine. That simplification is primarily aimed at avoiding having to deal with sockets in C++, not because it's any more. Actually, we're going to look at two different scenarios for doing socket connections and communicating. We've already talked about serialization, and that's what we've been using up to this point. But we're going to look at an example today where instead of passing objects, serialized objects, we're going to be passing bytes, arrays. So we'll be reading and writing byte arrays. Doing that allows us, provides for us language interoperability. And you'll need to do that to download a file because it's not a Java object. You'll be actually going out and reading bytes from a disk file, a binary disk file, either an MP3 or an MP4. So you'll read a buffer from the file and then write that buffer across a socket to the client, and continue to do that until you get to the end of the file. It's not necessarily the most efficient way to do an upload or a download, but on the other hand, it'll work just fine. It'll give you an opportunity to design your own protocol, a handshake between the client and the server, to make sure that the entire file gets downloaded to the client. So that's what we're aimed for here with this section. So in the section on network addressing, we actually were into the class notes and got as far as 3.b.8. So that's been a couple of weeks ago. We went through some of these examples: get IP, get name for IP, and these are all in this simple Java sock example. We looked at datagrams. No, actually, I don't think we did look at datagrams, but we did look at the browser, simple browser as well. Rather than going through the example on datagrams, I've got about 3 examples I'd like to go through today that show you progressively more more infrastructure, I guess the right way to put it, for doing TCP/IP connections and communications. So we'll probably skip datagrams, that example, and we'll do the simple socket server, client and server, which is in the Java simple sock. And then I also want to take a look at both of these examples. So the first example, JavaThreadSock, is a threaded socket server where the client and the server communicate with each other by means of serialization using an object input and object output stream. And then the last one, actually, simple interop, it actually contains code in 3 different programming languages. There's C++, C#, and Java. We'll take a look at just using the Java server. I think I provided a C++ server and client both, and the same thing, I'm sorry, not C++, C#. There's a server and client both. And then the C++, actually, that's not my code. It's from another author who actually has developed a very simple wrapping for C-based sockets in C++. There are several different libraries that you could use for doing socket TCP/IP in C++. And maybe one of the more popular ones is called the Boost library, which is an all-encompassing library, but we'll take a look at just a very simple client, Echo client there. The idea with this last example is to provide language interoperability, right? That's why it's called simple interop. We want to be able to have a server that's written in one language and clients that may be written in different languages. Before we do that, I just want to remind you again, this is probably one of the more important aspects of it. If you're working completely in Java, then in fact, any one of these 3 forms of streams is fine for TCP/IP connections. A buffered stream, a data stream, or an object stream. And remember the distinction between the 3 of them. A buffered stream is exactly that. You're essentially reading and writing byte by byte, but in fact, underlying that is a buffer. And the system takes care of the buffering for you. The Java runtime takes care of the buffering for you. The data stream, on the other hand, is intended for reading and writing primitive Java data. So if you're not doing any serialization of objects, only writing primitive data, then a data stream is the most efficient way to do that. And then the object stream adds another level of complexity, if you will. An object stream allows your reads and writes to be anything that's primitive, as well as so you can write an object or you can write primitive data. So an object stream provides the highest level that's available in terms of reading and writing. But then the requirement is those objects have to be serializable. And in this particular case, although you can customize serialization, as we talked about when we went through serialization, this is most commonly used with a binary format, with a default Java binary format for serialization. So actually, one more thing before we get into the examples. I did want to spend some time going over the scenario for stream sockets. And this is kind of based upon the classes in Java, java.net. In java.net, there is a class called server socket, and you create a server socket object specifying a port number. And that essentially binds the server program or thread, the server thread, to a specific port on a machine. And actually, that has to occur before a client can make a connection to it. So the server listens for arriving requests by calling the accept method on that port or on that socket, on that server socket. And the accept method is a blocking method. So it will sit there until a client actually makes a connection, makes a request, and a client makes a request by creating a new socket object. And the constructor for the socket, for creating a socket, includes a host name and a port. So it's a well-known address, right? This is the most common form of TCP/IP socket connections. And well-known address means that, in fact, when the client makes a connection to the server, the client knows both the IP address of the server or the machine name of the server, as well as the port on which the server is listening. After the client creates the socket and moves to the next statement, the client will not move to the next statement in its program, nor will the server move to its statement after the accept in its program until after a connection actually occurs. So at that point, the two executing programs are synchronized. And after that, each of them can use that socket, which is an active connection, can use that socket to request the input and output stream. So on the server side, you can get an input stream and an output stream. Obviously, you read from the input stream and you write to the output stream. And on the client side, the same thing, you get an input stream and output stream. So whenever the server writes to its output stream, correspondingly, the client will read from its input stream to receive the message from the server, and vice versa. And the order in which the client and server read and write is the protocol. That really defines the protocol between the client and the server. In a very real way, that's the way HTTP is defined. The server waits for a message in a given format, and it replies to that message. Every protocol is defined that same way. So let's take a look at some examples. And as I said, let's first go back to this Java simple sock. And the very last one of these, there's a socket client and a socket server. So this would be a good example of our first socket connection. I strongly encourage you as you develop your sixth assignment that you get these examples to work, primarily the interop, threaded interop assignment, but you may want to do it with all of them to make sure that step by step everything is ready on both of the platforms. Run it on both the Raspberry Pi, run the server on the Raspberry Pi, and the client on your development environment. So let's take a look at the code here. So this is Java simple sock, no threading, and it's the last two examples here. There's a socket client and a socket server. So in the top window, I have the client showing, and this is the main method. It's just a simple main in the class. It creates a socket, defines a string, which is the host. So in fact, it'll take an argument, which would be if you want the client to run on a separate host than the server, that argument would be the local host that comes in. And it just assumes that the port number is 8888, and the server assumes the same thing. So you can see that the client creates a new socket object by sock equals new new socket, specifying the host and the port number. And actually, in time, that should not be executed until after the server has actually gotten to this point in its code. So in fact, the server will create a new server socket specifying the port on whichever machine it is it's running. And then when it's ready to start accepting, then it does, based upon that server socket, server.accept. And it will return for it a socket object. Socket object, I guess the definition of it is above this window, but a socket object is the exact same thing that the client has. So once a socket is, once the server moves past the accept, then sock on the server side and sock, in this case I'm using the same variable name on the client side, have been defined, and we can now get the streams for it. So after the server accepts, then in fact on the client side we get the output stream, and we're going to define it as an object output stream. And in this case we'll write the string object high and then the integer object 100. And on the server side we're going to define an object input stream corresponding. Get that from the socket.get input stream to create our object input stream, and then we have to read in the same order that it's written a string, so in.read object, and that's going to get us the string, and in.read object again will get us the integer. So if I exchange these two reads around, I would end up generating an exception because things are going to arrive in the same order that they're sent from the server. So let's go ahead and build and run this example. So I'll run the server. I've got to have two LX terminals. One is going to be running the server, the other is going to be running the client. I could run the client on, or excuse me, the server on the Raspberry Pi, but I don't have it hooked up, so I'm not going to do that. So if I do ant build, and then java-cp. So I'm going to run the server here, classes. And you can see the server sends out its message, server is ready for 3 connections, server waiting for a connection. So here's server is ready for 3 connections, and server is waiting for a connection. So the server is sitting at the server.accept statement right now. And let's go to the client. And to run the Java client, since I'm running on the same host, I don't have to give it a host name. And now it's important to watch. Actually, I don't think there's any echoing that takes place in the client. It simply sends a message. So in doing the client, it created the new socket, which did the connection for us. It got the output stream. It wrote high and it wrote 100. And when the server received those messages, it actually indicated that it had received it. So the server should actually do this, since the server is in a loop three times looking for input, looking for connections. We'll run this 3 times, and you can see that the server did receive the 3 messages, and then that completed the iteration of the loop, so it stopped. The only point I want to make that motivates where we're going next is that suppose that I have multiple clients connecting to the server, and in fact, those clients, if the interaction between the client and the server, in other words, the execution of the code down here takes sufficient time, then in fact I may have multiple clients executing, the server accepting, the server waiting, the clients waiting while an interaction is taking place with another client. So if I have 2 or 3 different clients, in fact, those clients have to wait in line until any previous queued clients and server activities between the client and server communications between the client and the server are completed before they'll be accepted. And that's the reason that we use threading. So let's take a look at the example of threaded. So this is in the Java thread sock, and it is the first example on 3.b.9 Java thread sock. So let's take a look at the code there. And in this case, there is a threaded sock client and a threaded sock server. I don't think there's actually any threading in the client, but let's read it and find out. So let's get this guy in the same directory. And let's take a look at the code. First look at the client. Again, it's a class that has only a main. And in this case, we allow the invocation of the client to include both a host and a port. So we can change the port number if we want to, as long as the server knows what port it is, or we agree on both of them. So here is the blocking connection statement, creating a new socket, host and port number from the client, and the client will block at that statement until the server accepts. Then I'm going to, in this case, a buffered reader, standard in this is to read a line from the command line, and for every line from the command line, so I get a line number from 0 to 4, and I'm going to associate it with the output stream of the socket. I get this socket get output stream, and also create an input stream associated with the socket as well. And these are object input and output streams. So what I'm going to be doing is sending across a number from 0 to 4 and getting back from the server a string that is associated with it. So on the server side, we'll see here in just a minute, the server has a data structure, and it looks in that data structure, indexes it. I think it's an array of strings, and just indexes based upon the integer that comes across, 0 through 4. So while true, os.writeObject input string, in string. So the out stream is what's going out to my server from the client, and instr is in string is get the next token from the command line input. So if the user enters 0, 1, 2, or 3, then in fact that's what will be sent across. And then after, if it's an end, then there's a break. But if there's not, then it actually gets from the input stream is.readObject, and then it prints that object out. System.out.print system.out.print the object that's read from the server. So let's take a look at the server side. It's more interesting. So in this case, I've actually got a class that has that extends thread. There's a main method. So the thread has a single object within it. Actually, this is not a shared object. We could share it, but that's not the case. When I create a new thread object, I create this string array called buff, and it has 0, 1, 1, 2, 3, 4, 5 different things in it. This is just text from the textbook, and this is the constructor for it, public threaded sock server, where we get from so as a thread we're going to get the socket connection from the main method, and we're also going to get an integer which is an identifier of who the client is. So in fact, the run method is what does all the communication. So in the run method of this thread, right? So each time we get a connection, we create a new thread. Actually, let's go down and read that part first. The main makes better sense. So in the main, there's simply a while statement where we're doing two things: accepting a client connection. All right, server.accept. So server is a server socket on whatever port. And then each time we get a connection to a client, what we're going to do is create one of these server objects and pass, which is a thread, and pass that thread the socket and then a unique identifier for the client, for the connection, not for the client, for the connection. And then we start that thread. So in this case, the main method, which is the main thread of the program, does nothing more than iterate through accepts, and every time a client makes a connection to it, that connection, here it's a socket, that connection gets passed to the constructor for a new thread. So we make a new thread, and that socket is handled by that new thread. So every time a client makes a connection, we have a thread that manages that connection, and that connection may include multiple back and forths between the client and the server. So let's go ahead and execute this one. And let's run the server in this terminal. And we'll just use port number 2020. And now in the client, we have to tell the client that we're connecting to the local host, and again, the port number 2020. So now the client has an iteration here where we're going to enter the line number, or I think it's exit. So if I enter line number 0, then what the server is going to return for me is whatever string that was. So that string is the object class, also has support for wait. So let's look at string. We'll just go through one of them. If the timer has expired, the thread continues. This call can cause some overhead in programs. Notify signals awaiting thread to wake up. Notify signals awaiting thread to wake up. And 4 and 5, and actually we'll get an exception here pretty quick. Yeah. So it wasn't recognized over here, so the server gave up on that connection. So there you can see an example where we can have multiple clients actually communicating at the same time with the server, and I guess we should go through that scenario. So let's do that. So now we have 3 different windows going here, LX terminals, and let's run the client on So you can see now we have client 0 connected and a client 1 connected. And now let's do look for the fourth one from the first client and look for the 0th one from the second client. So I have 2 clients simultaneously connected. So how many threads are there running in the server at this point in time? Well, I've got the main thread that's still running. It's sitting waiting for more connections. I've got the first of our server, or excuse me, yeah, server threads and threaded sock server, and it is communicating and has a connection, an active connection with the client that I've just highlighted in the upper left. And then the third thread running on the server machine is communicating with the client in the upper right-hand corner here. All right, so we have connections to both of them currently active, and then on top of that, we're sitting. The server is sitting waiting for another connection. Is it end or exit? Yeah, it's end. So now there's one more to look at. I want to finish with a look at simple interop, and this one. You can see that there is a, well, let's look at the source directory. There's a C++ subdirectory in source, and as I mentioned, this is code that came from, whose implementation is it? I think it may be, if there's a readme.text, I might put it in there. Otherwise, I don't remember where it is. It should be in. Let's see if it's in this guy. Yeah, it's got the open source license in it. Copyright 2002, but it doesn't say who copyright belongs to. So I've got C++, I've got a C++ program. I also have C#. Actually, I don't have a server in C#. Oh, interesting, Emacs doesn't know about C#. So here is the C# program. I might have mentioned this in class. If you want to run this, it certainly should run. There's an open source implementation of C# that'll run on Linux. It's called Mono, and I'm quite certain that it's the repository that comes standard with Debian Linux Wheezy includes Mono, so you can sudo apt-get install Mono, and that'll include a C# compiler and a C#, the equivalent of a Java compiler and the Java command for C#, and this should run as one of the valid clients. And then there's in the Java directory, there's a threaded server. The threaded server looks identical to the server that we just read, in that there's a main method that with a while true, right? While forever until I get control seed. While forever, sock equals server.accept, and then create a new thread and start that thread and pass the sock to the thread. Right, so from that perspective, it's identical to the example we just looked at. The difference in this one is that in order to allow the communication between client and server to be language neutral, we need to communicate in terms of bytes. So in this particular case, even though we're only going to pass strings, this is doing echoes, so whatever gets sent from the client to the server gets sent directly back from the server to the client, an echo server. And it's a string. It's going to go both ways, but that doesn't mean we're limited to strings. We can pass anything that we want. Every class in Java has a get bytes, or excuse me, not every class, but there's a get bytes, so you can convert from whatever that object is or whatever that data value is to a set of an array of bytes. So the run method for the server's thread creates the output stream based upon the connection. Connection got sent to it. This is con is a instance variable of this thread object. which is nothing more than the socket connection. So we get its output stream, we get its input stream, and then we create a byte array, and that's what we're going to use to go back and forth with the server. I'm sorry, with the client. And the client string is a new string, right? So what we do is read in sock.read into our byte array, beginning at subscript 0 in the byte array up to 1024 bytes. And after we've gotten that, we convert it into a string. So new string of a byte array beginning at 0. And how many bytes? Well, the number of bytes that I got from the read. So when I do a byte read, I have to give it a byte array to read it into, and it's going to return for me the number of bytes that actually got read. So I convert that into a string, and then since I'm an echo server, I write out the exact same thing that I read, and then I read the next input from the client. So as long as the client doesn't send me more than 1024 bytes, this works just fine. If they send me more than 1024 bytes, then in fact the code would get tripped up here because I'd end up trying to do another read before I've completed reading, trying to do another read before I've gotten all of the, I've done a write and then another read before I've gotten all of the information from the client. So let's go ahead and execute this one as well, and I want to execute it in we'll do the server in the lower right just like we've done before. And let's build Java first. And let's start the Java server. No, it's not echo client. Must be threaded echo server. And we'll tell it to listen on 2020. And now let's go ahead and execute, we'll build the C++. And you can see in the, there's an echo in the ant build for the C++ that gives me the syntax for invoking the C++ client. So in the bin directory, C++ client, localhost, since the server is running on the same machine, and then a string. I am a string, and 2020. So what's going to happen is the client is going to send this string to the server. The server it expects the server is running on localhost and listening to 2020. And then it receives a string back. I am a string, so to make it simple for the input, I didn't put any spaces in the string. I think it just reads it as one argument. It expects 3 arguments for the input for it. So here's I'm another string. And you can see the server actually responds. So now let's go ahead and run also the Java server, Java client. And Java-CP classes. And I think this one is, yeah, this is an iterative one. So hello from the Java client. And I got that back from the server. I echoed back what it sent me. they were talking about interoperable TCP/IP connections that use threads. Okay, so there you can see I can communicate equally well, and again, it's not limited to strings. I can pass well, I can pass anything that I want, right? So in particular, if we wanted to, we could use TCP/IP as opposed to using an HTTP connection to implement JSON RPC for that matter. By sending a string back and forth, or we could take a byte array and put into it any other of the primitive types or any other type that we wanted of information. Okay, so I'm going to leave it at that. I think it's end to get out of that client, and let's get rid of that. And I think that is the end. Yeah, that's the end of the section on sockets in Java. If you're interested in C#, there's a section here that covers sockets in C#. Both datagram and TCP sockets as well. So I'm going to leave it at that for today.